And now we'll look at power loss protection. Specifically, we want to know how is data protected against power failure, as well as failure of any individual component in the system. Extreme I/O uses a combination of system DRAM, that is the memory in the storage controller, and an external, uninterruptible power supply. Any pending data and metadata updates are stored in DRAM on two different controllers. Any dirty data gets aggregated and written to RAID stripes in the background. Each unit gets plugged into two separate battery-backed units so that even if one of them were to fail, there's still battery protection for the entire cluster. This is similar to the Dell EMC VNX product, except that has an internal battery-backed unit and Extreme I/O has an external one. On power loss, any dirty data gets flushed to the disk shelf or to the internal controller SSDs. The behavior in the case of a single battery-backed unit failure is unclear. We couldn't find any documentation about how that works, but presumably the storage array continues running. SolidFire and Pure use an NVRAM solution. Each node or each controller has an internal NVRAM cache. That's PCIe in the case of SolidFire and NVMe for Pure. Each cache has ECC DRAM plus a supercapacitor for power loss protection and some SLC flash that can be persistent. All data and metadata writes are committed to multiple NVRAM cards. In the case of power loss, the card automatically persists the data to flash, and then when power is restored, writes that flash data down to DRAM. In summary, again, we have two different ways to solve this problem that are used by the three vendors. If we look at Extreme I/O's use of DRAM and external power, what we get is the highest throughput and lowest possible latency. The data itself is protected on two controllers and protected from a single point of failure. However, there is a risk of software data loss if the kernels were to panic on both controllers at the same time. This is a very simple implementation. You have to have power to DRAM at all times, so Extreme I/O simply brings their own power. This is best for performance and best for ease of engineering. On the NVRAM side, we have high throughput and low latency, but not nearly as high as with DRAM. The data is protected from a single point of failure and abstracted from the software so that it's protected in case of software crashes. This implementation is really low maintenance and is best when we're trying to find the highest possible levels of protection.